Goderis, and I'm an MSGC undergraduate research fellow for this summer. And this past summer, I worked on the alignment, accuracy, and feedback control in high altitude quantum communication systems. The problem that this project this summer is trying to solve. So as you can see, we have two balloons in space that are moving independently of each other in 3 axes. And so this project aims to solve what we consider as the pre-com layer of aligning these two balloons in space so that we can then quantum communicate between the two balloons. Solving this problem is immense for quantum communication and is a massive stepping stone into creating a quantum network as well as a future quantum space communication. So some goals for this summer. So my first goal was to create a randomization loop for a legacy balloon alignment model in Simulink. Improve upon the legacy model by incorporating realistic Gaussian beam dispersions. And then also look at incorporating algorithms for super resolution imaging that could help us achieve our 1 arcminute goal for accuracy. So the process flow that I approach the randomization of the balloon for is as follows. So first off, I had to determine the degrees of freedom for our alignment motors. Then I had to set boundaries for the locations of balloon 2 with respect to balloon 1. As you can see in this picture here, this is what happens when the boundary is set incorrectly. And then create a random position for balloon 2, and then kind of going hand in hand, checking if communication is possible. So here's like a small snippet of my MATLAB code that I used, and this randomized a position of balloon 2, and then it did some math in spherical coordinates and checked if balloon 2 was in motor range of balloon 1. And then after that was all said and done, perform the alignment in a simulation for balloon 1 and 2. At the Simulink model in action. So here's an image. This is balloon 2's base, and as you can see, balloon 1's beam just whizzed by. Eventually come back and begin to align with balloon 2. Here you go. And after about 15 seconds or so, it reaches steady state operating, and so the balloons are now aligned with each other in space. So future work for the randomization of the balloons. So include the spin of the balloons in simulation. So this is only a 3-axis randomization position. Create an algorithm to align the telescopes on the balloon. So this is taking into account that the telescopes are always pointing at each other, which obviously in the real world that isn't the case. So we would have to simulate a way to determine which way the telescopes are pointing on the balloon base. Use latitude, longitude, and elevation for locating the balloons in simulation. So currently I just have an arbitrary XYZ coordinate system to keep things simple, but for future reference, we would obviously want lat, long, and elevation. And then finally, creating a physical model. So taking these lessons learned from the simulation and port it to a physical model that would be able to receive location data from a ground station and or a GPS satellite. So now diving into how I accomplished the next goal of Gaussian beam dispersion. So originally when I took over this project, the alignment of the beams was kind of just a point-to-point model. So there was no taking into account the losses associated with a Gaussian beam. So the first step was to create a Simulink code to calculate the actual Gaussian beam itself. And then the next would be plotting a intensity in the electric field from the model. And then using that data to calculate the intensity at a 1/e drop off in intensity. And then take that and find the radius of the balloon at that 1/e intensity, since that is the usable part of the beam. Look at the first dispersion pattern that we were trying to take into account for at distance, and that is the growing beam waste of the beam at distance by the rate of WZ. And then this then creates a spot size of this red circle right here at a distance, at whatever distance we're trying to communicate at. And then we're also trying to take into account the transverse beam dispersion of the changing intensity of our spot size as we grow away from our center point of the beam. So here is a look at the results. So this is all calculated from Simulink, and I created it so that it was portable to like different lasers. So all you would have to do is upload a different MATLAB file with your laser specs, and then the Simulink would be able to handle the math itself. It's all internal to the Simulink model. Super resolution imaging. So throughout the summer, I was looking toward the idea of determining bright spots of the beam using pixelization. So this would be able to determine the usable portion of the beam at the receiver versus doing the 1/e drop off in intensity. And I spent time exploring some pixelation strategies, mainly in the source that is provided below, which they separate the bright spots of a beam into different pixels, and then we could determine which parts of the beam that we want to use to transmit data. Why does this work that I participated in this summer matter? So I guess 3 key points for why this work matters. It would provide ultra-fast and secure intercontinental communication. So obviously you're not going to be able to communicate from New York to China with 2 weather balloons because of the curvature of the Earth, but LA to New York is something very possible, and this work would provide that as a possibility in the future. It's also a stepping stone on the road to a quantum communication network. So by proving that we could possibly use quantum communication in the upper atmosphere, that would be a stepping stone on the road to having satellite to satellite quantum communication. And then we would be looking at something that we could talk from New York to China with. And then also a simulation of space quantum communication at a lower altitude. Obviously, we all know that going into space and trying things is very expensive and time consuming. And this provides a very similar atmosphere, no pun intended, but to practice space communication at a lower altitude. Thank you for your attention. Had a great summer, and thank you for this opportunity.